Thanks for coming to this talk, hope everyone has had a great reInvent so far. Enjoyed the sessions. We assure you we've saved the best for the last. So just to get started, my name is Vaidi. I've been with AWS coming up on 5 years. And the last 2 years, I have had the pleasure of leading the team that supports Netflix data platforms. And today it is my honor and pleasure to welcome our next two speakers for today. Ashwin Kayur and Rakesh Veeramachineni. They're both software engineers within Netflix's Big Data Compute org. And together, they will describe the journey Netflix took to modernize their data lake using Apache Iceberg. Apache Iceberg, as I'm sure every one of you knows, is one of the more popular open table formats that was invented by and at Netflix to help folks efficiently manage data lakes with transactional compliance. So your queries could travel through time while your schemas and your businesses evolve. And I'm really looking forward to listen to a few things. Obviously, I want to listen to the problems that necessitated the move to Apache Iceberg. I want to listen to the scaling challenges Netflix faced and some of the feature sets and the tools that they invented along the way to deal with those challenges. And last but not the least, I'm definitely looking to listen to the impact of a lot of this work, both within and beyond Netflix, speaking of which, a lot of this work that Netflix is doing is informing AWS's own roadmap in the space. And since all of this work is out in the open source domain, I'm sure many of you will be able to take some valuable recipes to go home and implement within your own company. So without further ado, Ashwin, is all yours.
Oh. Thanks a lot, Vaidi. I would, first of all, a big shout out to AWS accounts team for all the support and partnership they provided in this journey. Myself, Ashwin Kayur, I'm a senior software engineer at Netflix. I'm part of data platform team, and at Netflix, I spend my time architecting solutions to manage and process large amounts of data using big data frameworks like Spark, Trino, and Apache Iceberg. I also actively contribute to these systems internally. Currently, I'm leading an effort to migrate from Hive-based data lake to an Iceberg-only data lake. And we'll be talking about that in this talk. I will let Rakesh introduce himself.
Thanks, Ashwin. My name is Rakesh. I've been at Netflix for about 5 years now, and I've had the privilege of working across the stack of our big data compute platform, from the metadata services layer to the storage layer to our compute engines. And most recently, I've also been working with Ashwin on leading an effort to sort of migrate all of our Hive data to Iceberg. And we're excited to share that with you folks today.
Here's the agenda of this talk. We will first begin by describing Netflix's overall business motivation. And then I will provide a high-level overview of our foundational data platform that powers all the customers and customer-facing features on our streaming platform. And then we will shine light on why we invented Iceberg and decided to make it a paved path within Netflix. And we'll also describe all the ecosystem that we built around Iceberg that helped us improve our underlying data infrastructure. Till recently, we have been predominantly a Hive-based data lake. In the next section, I will describe the infrastructure that we developed to transition into an Iceberg-only data lake. In conclusion, we'll provide key takeaways, and we'll also share our thoughts and key learnings with broader community. As you all know, Netflix stands as a premier entity in the realm of entertainment streaming. At Netflix, we dedicate significant amount of resources in comprehending our users' preferences. This includes understanding our users' favored movies or shows, as well as predicting the content that they might be interested in viewing in the future. So all the features, all the numerous features in our platform that you engage with and experience are all driven by data. For an instance, the top 10 movies or shows that you see are all derived by crunching the region-specific viewing statistics, as well as the thumbnails that you see is very intimately personalized to user interests. In a similar vein, our machine learning algorithms process vast amounts of user data to tailor user experience to a particular individual user. So all of these features that you see are all very closely personalized to user interests. All the teams within Netflix that work on these intriguing data-driven algorithms, they all depend on our foundational data platform. Data platform at Netflix offers a range of services. For instance, online data stores, compute and storage services that rely on AWS's S3 and EC2 primitives. Platform also provides other auxiliary services such as scheduling service that helps orchestrate large number of workflows. Above this foundational layer, data platform implements and provides us various high-level abstractions and systems that essentially helps us to orchestrate large number of jobs as well as to process data in multitude of ways. Next, Rakesh will double-click on this and provide us more details, in-depth details about our big data platform architecture.
Thanks, Ashwin. So this slide gives you sort of a high-level overview of all of the abstractions that we have in our big data platform. Over the years, we've sort of built out a cloud-native, extensible architecture sort of centered around principles like storage and compute separation and data platform component composability. With these principles, like we mainly had to lay these down because, like Ashwin was saying, data is central to everything we do at Netflix. And the big data platform actually powers Netflix through all phases of the business, all the way from internal analytics dashboards to A/B testing to even product-facing features like the top 10 titles that you see on the website. And as such, we do collect tons of data from our online data stores that you see on the left there. Cassandra is used quite widely for all of our member-facing websites. We have RDS and we have CockroachDB. And we have CDC streams set up from all of these online data stores that are processed by our stream processing platform that we call Data Mesh. Data Mesh is composed again of open source services like Flink and Kafka. And Data Mesh pretty much processes trillions of events per day from microservices consuming data from these online data stores and lands tens of petabytes of data each day into our warehouse in S3. Caspactor is also another homegrown solution of ours. It basically is responsible for taking snapshots and backups of Cassandra tables that we have running on our online websites and dumping them into Iceberg tables in S3. So looking at the bottommost layer in the abstractions we have there, the lowest layer, all of our data sits completely in S3. We have hundreds of petabytes there that's growing at like a very fast clip. And for our compute needs, we use Titus, our homegrown container platform, but that in turn also runs on EC2 instances. In addition to that, moving next, we have the metadata services layer. So the metadata services layer sort of abstracts out all of the storage details from our users into that of a table format. So all of our tables are Iceberg formatted at the moment, but we used to be partially in Hive and in Iceberg. And as part of our effort, we've sort of moved towards one of like mostly Iceberg. And we also have Metacat here, our metadata services layer. Metacat basically provides a unified API for accessing metadata about our data sets. And it does so by abstracting away all of the data stores that we support at Netflix, and users just come using like a three-part qualified name when querying their table, and they're like agnostic to the underlying details of the table, like the table type and the storage type and things like that. So for example, they use a table name like prod/foo/bar to come and query everything they need to know about that table. And in the metadata services layer, we also have services like the Netflix data catalog and the policy engine. These two services form like a key pillar of our governance platform. they essentially index all of the data sets that we have within Netflix. Not just the big data sets, but all of the data sets. And the policy engine enforces policies like, hey, every data set should have an owner. And if a data set has classified information, it has to be annotated as such. On top of the metadata services layer, we have our compute engine layer. As you can see, we use like a myriad of engines. Spark is mostly used for ETL, batch processing. We have thousands of jobs running on our platform every day. Trino is mostly used for interactive analytics. And Druid is also used quite heavily for our real-time aggregated dashboards. This is just, again, a subset of the engines, but the most used ones. And on top of our compute engine layer, we now have our client-facing tools. Here, again, we provide a suite of tools to sort of fit all of the personas of users that use our platform. All of the users of our platform are internal to Netflix, but they come from different areas, like you have analytics engineers, we have data engineers, data scientists, and so on. So in our tooling, we have a data platform where a user could just come in, start running some SQL, and running some queries against the engine of their choice. We also have Tableau, which is used quite widely for our dashboarding. And we also have Jupyter that's used quite a bit by our research engineers and data scientists. This is just, again, just a subset of the client-side tooling that we support. The control plane and data plane abstractions that we have between the engines basically allows for both our users and us as a platform to allow users to bring in their own tools that they see fit and connect seamlessly to the engines. And it also abstracts them away from the specifics of the engines, like the versions, deployments, and so on. With that, just a little bit of history. So we started by moving from an on-prem architecture to the cloud at around 2010 or so. And we were following these principles like I was mentioning earlier. And we were mostly a Hive sort of warehouse, a primarily Hive formatted warehouse. So at our peak, we had about 600,000 Hive tables and 250 million partitions or so. But we soon started running into limitations with Hive. As perhaps most of you are also aware, there is no ACID semantics out of the box. So we had to build like our own patterns to sort of get around that. Additionally, like some of the tables in our warehouse started growing into petabytes of size. And every time, say, a data engineer had to go and change the partitioning scheme or schema of a table, they had to pretty much drop and rewrite all of the data in that table. So it was getting to a point where basically running a platform completely on Hive was not tenable. That's when Ryan Blue, Dan Weeks, and team sort of designed Iceberg, sort of another open table format with the community in mind, and something that has well-defined interfaces and contracts and works across a variety of languages. So Iceberg not only sort of overcame some of these drawbacks that we had with Hive, but also introduced an additional set of features. So to begin with, ACID transactions were available out of the box. And then one of the unique features of Iceberg is that the rich metadata layer that's available. So you can get the full footprint of a particular table just looking at the metadata layer. So this is quite powerful because you can not only speed up your queries, but it also eases any sort of data management and governance operations that you want to do on your table. And some other features are like storage separation or configuration of tables that you get. This basically enabled us in the platform to allow users to configure tables and not jobs. For example, users can go and configure a table to have Z-standard compression with like a certain split size and not have to go around configuring all of their jobs that write to this particular table. So that was fairly useful. Similarly, we have time travel, where you can query a table from a particular snapshot. This is used quite a bit by our data engineers. And similarly, there is partitioning evolution that is also supported out of the box. And Iceberg was built with a good set of pluggable and extensible interfaces. For example, like the table operations API, sort of made it easier to start integrating Iceberg with the engines that we had in the platform at that time. So we integrated it with Spark and Trino. And while we still had our Hive warehouse up and running in production, we started building out our Iceberg ecosystem in parallel. So we were primarily able to do this, and shout out to our architect at that time, Charles Smith. We put in like a good set of high-level abstractions that basically enabled us to build out this parallel Iceberg ecosystem to that of that is equivalent in feature parity with Hive without any disruption to our users. Say, for example, having like a high-level metastore layer where the users were abstracted away from the underlying table details. We basically started having our users create Iceberg tables by default, for example. So in terms of our journey, once we had Iceberg integrated with our engines, a few teams started using Iceberg quite a bit, and they were completely on board. And then we started building out the rest of the service ecosystem that we need for Iceberg to maturity. And I'll go a bit into the details of how we actually built each of these services and the why. And the reason we're doing that is because our hope is like this will help you reason about any sort of abstractions you might want to build out in your organization. These services are completely built on open source Iceberg APIs that are available today. So starting with the metadata services, as I was saying, Metacat is our primary federated metadata store. It provides not only a unified API, but also a unified type system when you're interacting with the data stores that we support. So it's not just the Hive metastore where we used to store our Hive table metadata, but also third-party stores like Snowflake. And having an abstraction like this basically, unlocks use cases where a user would want to write a transport job between Hive and Snowflake. They then would not need to be aware of the intricacies or the schema differences between Hive and Snowflake, for example. They would just deal with the canonical types that Metacat provides, and they would use that to write the transport jobs that they need. And Metacat, under the covers, takes care of translating between the specific data stores types. So with this abstraction in place, we started off by actually storing the Iceberg metadata that we need directly into the Hive metastore. So we wrote some custom APIs that did like a check and put operation to sort of keep track of like the most up-to-date state of an Iceberg table. But we quickly started running into some scalability issues, especially on the Hive side. Like I was saying, we had about 250 million partitions at that time in MySQL RDS instances that was backing our HMS. And with that, we had basically noisy neighbor issues where, say, a user would do a bulk update of a table with like 20 to 30 million partitions, and that would lock up a bunch of tables. And Iceberg has like an optimistic concurrency commit protocol. So you would have Iceberg tables that are constantly trying to commit to the table, whereas Hive tables have more of a pessimistic locking approach. So these sort of competing commit patterns ended up putting too much pressure on our RDS instances, basically. And this basically led to unavailability of Iceberg tables in our platform. We tried different things like scaling out or sharding our Hive metastore instances, but we, again, started hitting resource limits on MySQL. So that's when we decided to build Polaris, sort of a custom metastore designed specifically for Iceberg tables. Iceberg tables pretty much need a very simple data model. All you have to do is you need to keep track of the most recent root metadata JSON file for a particular table when you're committing to it. And every time you commit, you keep incrementing that, and you store just a pointer to it in your database. And we decided to go with CockroachDB in this case because our operations were mostly point updates, and CockroachDB provides horizontal scalability out of the box. And one more thing we added to We added to Polaris was also support for the Iceberg REST catalog spec. So the Iceberg REST catalog was like recently introduced within Iceberg, relatively recently introduced. It basically standardizes how Iceberg table metadata operations should be managed. It provides consistency around how the Iceberg commit protocol should work and say how Iceberg tables should be created in general. And the power of such a standardized interface basically allows you to sort of implement something like this in-house on top of your Metastore, and that is what we did. We added a layer of like REST catalog support within Polaris itself and started supporting the REST catalog endpoint. And with an endpoint like this, any third-party engine that can actually speak the standard can now start connecting to your warehouse directly. This is something that we did not have in the Hive world. You basically have now like a singular endpoint with which you can connect to your warehouse and start running queries against it. So this is quite powerful in that it even avoids vendor lock-in to a much larger degree because you not only control all of your data, but also the metadata and the Metastore operations. Some other nice things that the Iceberg REST catalog brings is when you have like a centralized catalog server running, you're basically in a position where you can start doing some optimizations to Iceberg's commit protocol itself. So for example, the Iceberg REST catalog helps with deconflicting commits. So the protocol itself is built with a change-based API. So that way, you do not have commits which do not conflict with each other. You can detect them instead of, like, say, failing one commit and then having users retry. This is problematic, for example, when you have tables that are being written to by tens of writers in parallel. And if these commits, today what happens is if these commits actually, even though they do not conflict with each other, they're not aware, and they end up having like others keep retrying, which is like pretty inefficient when you're operating Iceberg at scale. So this definitely helps with that, where if you're doing a schema update, you need not reject any writes that are happening to data files, for example. So that is sort of wraps up like the REST catalog sort of advantages, and it's something you should definitely look into. If you already have a Metastore, you can simply add an implementation of it on top of your Metastore. Next, we have our table management services that we built out. So once you start landing data into your warehouse, it's time to start thinking about the life cycle of the data. So to that end, we have processes called the janitors that essentially clean up expired data. We run it in like 3 flavors. We have TTL janitors that clean up data that is past a certain date of expiration. And this date is configured by our users, although we have some guidelines in place. We have snapshot janitors that clean up Iceberg snapshots based on a specific TTL. And we also have orphaned file janitors that clean up dangling files that land up in your bucket, but say do not belong to any Iceberg tables. These are basically files from failed commits and so on. All of these janitors are again built on open source Iceberg APIs. The snapshot janitor, for example, uses the expire snapshots API, and the orphaned file janitors uses the Spark Actions API that's available. So you can design APIs. You can design services that fit your needs. And this is a high-level overview of the architecture of how we run the janitors. So on the far left, a user basically goes through our portal or one of our engines and configures the TTL for the janitors. And let's say we take the snapshot janitor here as an example. These janitors run as a pool of Spark processes that are periodically scheduled. You can think of it as a service that's maintaining a pool of these Spark processes. The snapshot janitor then expires all of the irrelevant files that belong to a particular table, sends them out to an SQS queue. And then we have a deletion service that's running that makes sure that we're not over-deleting any of those files. And the deletion service basically pulls all of the files set up for deletion from the SQS queues, sends them out to an audit log. That's basically a streaming table of ours, and also goes to S3 and soft deletes the data. Before soft delete the data, and this audit log basically helps us restore the data whenever we need it. And it also keeps track of any cases where a user might have like accidentally dropped a table and they want to restore and recover it. And the soft deletion period is usually 5 to 7 days in our case. Similarly, as users write to their tables using a variety of engines, they might not be using the most optimal sort of format for writing out files. For example, some Spark jobs write out too many small files to Iceberg tables. And this is especially a problem for remote storage systems like S3, because you'll now have to incur the cost of network latency as you switch between I/O handles. So too many small files are a problem for compute engines. And in general, there is an optimization problem here where you can optimize the layout of files for a particular table in S3 in a way that is efficient for querying through engines. So that's where we implemented Autotune. Autotune runs in the background, completely abstracted away from our users, and sort of optimizes the data files that belong to users as tables. Some of the techniques we use are like, say, merging too many small files and rewriting them into files of like a reasonable size, sorting, row-level delete file compactions. And again, all of these use Iceberg OSS APIs. So it's something you can build on top of readily today as well. The architecture for Autotune is also a bit similar to that of the janitors. We leverage Spark here primarily as a distributed computation framework, more so than data processing. So if a user writes to Iceberg tables, the metastore is made aware of it, and then it sends an event to SQS saying that, hey, this table has committed these snapshots. Autotune sort of listens to those events. Let's say in this case, it is running in a compaction mode. It has a compaction config stored with all of the heuristics on to what degree files should be compacted and so on. It then spins off a Spark job to go and rewrite the data files that belong to this table in accordance with the config, and then commits that back to the Iceberg table. Similarly, Autolift is another service that we've built specifically at Netflix. The motivation here was that most of our engines are only in the US East 1 region. However, we do have streaming engines that write using Flink to remote regions. So this basically leads to pretty costly cross-region bandwidth costs. So to avoid that, we built Autolift that basically localizes files from these remote regions to US East 1. It localizes about 2 to 3 petabytes of data each day. And the way it also works is it basically scans a stream of incoming snapshots, figures out all of the files that need to be localized, and then makes use of the Iceberg replace commit API to basically remove the remote files and then replace them with local ones atomically. So again, this is an abstraction that we built on OSS APIs. Another sort of new feature that we added on top of Iceberg is secure Iceberg tables. So the way in the Hive world, our warehouse was pretty much open for all. But teams who wanted security would basically have specific S3 IAM roles that they would set up, and that specific folks on their team would have access to. But this sort of went against our ethos, where we wanted users to just interact with high-level abstractions in our platform and not have to deal with things at the S3 layer. So that's when we decided to leverage Iceberg and the metadata layer available to build security across our warehouse and have like a secure data warehouse by default. I'm going to give a quick overview of how we built security into our Iceberg tables, but the actual implementation is a bit involved. So in the interest of time, like if you folks are interested, I'm happy to chat after the talk and give you more details. But at a high level, how this works is we've modeled each table as a resource that needs to be secured. So we basically have table level security, and each table is mapped to a specific prefix in S3. So for example, table foo, all of the data and metadata for table foo lives in an S3 prefix, S3/prod/foo, right? And all of the ACLs, like all of the users that have access to this particular table, that metadata is also stored in the Iceberg table. So the end-to-end flow would basically look like a user Alice would come to query table foo. The Spark driver would then go and talk to an external signer service. So this signer service is basically a neat abstraction that we built that acts as the policy enforcement point for our secure tables. What the signer service does is whenever Spark comes to it to check that, hey, does user Alice have access to table foo, it loads the table from our metastore, checks if this user is there in the ACL list, and hands out an STS token. So it basically acts as like an interceptor that's external to engines. And the nice thing about that is we were able to now extend the signer service to our other engines like Trino as well. So once the Iceberg catalog has the STS token, it sort of passes that down to the Spark executors to read. So the overall access model that we have is pretty simple. Users have like either read, write, or admin permissions to the table. It's not a full-blown RBAC framework with role hierarchies and so on. And we also do not support row and column level security yet, although we are seeing requests from some of our users for these use cases. And on the right, you can see like what the data model for ACLs looks like. It's the user and their permissions. And all of this is stored in the Iceberg root metadata JSON file itself as a property. So to wrap up, as you can see, we started building out these secure Iceberg tables, started leveraging some of the performance and efficiency gains that we get from Iceberg, thanks to these high-level abstractions we had in place where our users didn't have to be aware of the fact that, hey, I actually have a Hive table or I have an Iceberg table under the covers. However, at the same time, we still had hundreds of petabytes of data that was still in the Hive format. That's when our users simply did not have enough bandwidth to start migrating all of that data into Iceberg. So that's when we decided to start a managed effort where we would build migration tooling that did that heavy lifting on behalf of our users and sort of migrate all of these tables into Iceberg in a transparent manner with minimal downtime. And Ashwin will talk a bit about the migration tooling that we built to make that happen.
Thanks, Rakesh. Given the immense size of our data warehouse, where we have very high multiples of hundreds of petabytes of data, coupled with large number of tables that we have, where we have about 1.5 million tables, the task of migrating from a predominantly a Hive-based data lake to an Iceberg-only data lake is a colossal undertaking. To deal with this challenge, we started designing our Hive to Iceberg migration tooling with certain key objectives in mind. Firstly, because of this huge, immense size of the data warehouse, we wanted to minimize the overall data movement during the migration. This is to reduce the overall migration time as well as to bring the migration costs under control. Second key objective is to minimize user friction, where we wanted to understand and anticipate beforehand what are the different ways users will experience issues during or after the migration and want to minimize them. In the similar way, we wanted to ensure business continuity, where we wanted to, again, anticipate all the serious incidents that could happen during migration and after the migration. And we tried to mitigate them by developing certain features in the tooling. To address first key challenge, which is to minimize overall data movement, we designed and implemented a Spark SQL procedure, which essentially, when you run this Spark SQL procedure on a Hive table, then it creates a Iceberg metadata on top of the data files pointed to by a Hive table, instead of copying the data from Hive to Iceberg. For an instance, this procedure begins by extracting the data files corresponding to a Hive table, and then it builds layers of metadata. For example, we create a set of manifest files. Each manifest file points to a set of data files specific to a partition. And then on top of this, we create a set of manifest list files where each manifest list stores metadata belonging to manifest files, including all the partitions handled by a particular manifest file. So each manifest list corresponds to a snapshot, and this is pointed by metadata file. So when a user accesses a particular Iceberg table, then it goes through Iceberg catalog, which will have pointer to the latest metadata file. So we have migrated about 95% of our non-temporary Hive tables using this technique, where it creates Iceberg metadata instead of copying the data. But I want to mention that only very small minority of the tables we had to migrate using the copy operation. In the upcoming slides, I will talk about what are those scenarios where we had to perform copy operation to perform migration. To achieve the second objective, second and third objective where we wanted to minimize user friction and ensure business continuity, we developed a Hive to Iceberg migration tooling. So this tooling helps us in providing a managed migration for our users. So in this tooling, we essentially devised 5 different components, each component bearing a unique responsibility. These components, they interact with each other through a shared state, yet they all work asynchronously by not blocked on each other. So each component can be invoked using a workflow that wakes up, performs a certain job, and then goes to sleep. For example, the processor wakes up, and then it looks at all the tables that are scheduled to be migrated, and then it extracts the table metadata such as the list of table owners, list of downstream users, so on and so forth. And then it prepares these tables for the migration. Next, the communicator component looks at these tables. It sends the communication emails to this list of table owners and and the downstream users to notify them about the upcoming scheduled migration, as well as the current state of migration and what to expect next. Whereas the migrator component itself performs the actual migration of the tables, the scheduled tables, from Hive to Iceberg. If the migration is successful, then we finalize the migration, or if a user experiences an issue, then reverter steps in, and then it reverts certain tables back to the original Hive table format. Now, to guarantee an instantaneous revert operation and to unblock user as soon as possible, we make sure that original Hive table is in sync with a newly created Iceberg table for some period of time after the migration. Now, this is ensured by the shadower component, whose responsibility is to keep the original Hive table in sync with the newly created Iceberg table. And we perform this delta copying using the metadata layer provided by Iceberg. Also, I wanted to mention that to increase the velocity of our migration, for each component, we spin up multiple instances of this component, and we distribute the list of tables to these instances using consistent hashing. So that way, we are able to do this processing in parallel. Our migration tooling relies on several external auxiliary services. For example, it relies on this lineage logging service, which is essentially a service that provides a centralized store that stores the flow between all the different data systems within Netflix. So our preprocessor component uses this service to extract certain lineage metadata, such as who is the list of table owners, who are the list of downstream users, so on and so forth. And then we use another service that Rakesh spoke about, which is a Metacat. This is our federated metastore that stores the metadata about all the different data sources within Netflix. So migrator uses this service to perform various operations on the metadata layer, such as blocking and unblocking table during migration, or the table renaming, or copying certain important metadata from original Hive table to newly created Iceberg table. There is another similar service called as, we call it NDC, Network Data Catalog Service. And this is a service that also stores other auxiliary metadata pieces within this service. Migrator uses this service to copy other pieces of metadata information from original Hive table to newly created Iceberg table, such as table owners, data classification, table size, TTL, etc. Essentially, idea is to hide the fact that you have migrated the table and make sure that table looks as it was before. We designed the migrator in the form of a state machine, where essentially when you migrate a table, it goes through a set of states where we initially prepare the table for migration and then block the writes on it, migrate the table to Iceberg, then make that Iceberg table primary by swapping the names, and then unblock the table, primary table, and then archive original Hive table. If everything goes well, we finalize the migration. If something goes wrong, then reverter sends the table to a different set of states where we eventually revert the table back to original Hive table and then archive the newly created Iceberg table. So this way of designing a state machine-based migration tooling provides us with several benefits. For example, it lets our users have access to the current state of migration. So the tool will become completely transparent to the users, where they are always updated on what's the current state where the migration is at this moment and what to expect next. Secondly, whenever there is an exception, whenever we hit an exception at a particular state, then we can either go back to previous good state or we can move forward to next state once we debug and resolve the exception at that particular state. So this provides us with greater debuggability, also provides operational flexibility because we could roll back to previous good states. Also, this kind of design also helps us to ensure that each state follows a particular property. For example, we made sure that each state is idempotent with respect to a particular table, and this ensures that tool is retriable as well as so that whenever we retry, the outcome doesn't change on a particular table. Also, we are easily able to add new states to this state machine based on if we need to handle certain new corner cases or we want to handle new use cases. So that gives us immense extensibility. As I mentioned before, to guarantee an instantaneous revert operation, we keep the original Hive table in sync with newly created Iceberg table. We achieve this by making use of the metadata, changed partition metadata stored in Iceberg metadata layer. So for each changed partitions in the new table, we delete the data from the corresponding partition in the original Hive table and insert the data from changed partition to the original Hive table. So this way, we are able to sync both the deletes and inserts that happened after the migration to Iceberg table. And at the end, we set the watermark to latest snapshot in the original Hive table so that we could keep repeating this operation for some time after the migration. We encountered certain user friction points during the migration, and we handled them in a few different ways. For example, Iceberg doesn't support certain legacy features, such as data which is in CSV or text format. So for this case, so essentially what this meant is that we could not build Iceberg metadata on top of the data that was in this legacy format. So for this case, we had to copy the data from Hive to newly created Iceberg table. But these were very small minority of the tables, so it still was a win for us to do this. And so second issue is the legacy primitives. For example, if a Hive table has a data column which has a legacy type, such as timestamp is not the legacy type, but in Hive world, the timestamp underneath it gets translated to int96, which is considered a legacy data type in the Iceberg world. So even in this case, we had to copy the data from Hive to Iceberg. And there are certain nuances when a data column has not null attached to it in the Hive world. In the Iceberg, when we translate this into Iceberg, we get some kind of exception. So we had to make some fixes in the Iceberg library to deal with this. Then we came across very interesting set of tables within Netflix where these tables coordinate reads and writes between them. So what that meant is we could not migrate these tables independent of each other. So we had to find all the jobs associated with these tables, stop all the jobs, and then migrate all these tables at once, and then unblock these jobs. The third issue was that Iceberg being a paved path within Netflix, we had implemented security features on top of Iceberg. So we anticipated that once we migrate the table to Iceberg, users are going to have friction with respect to access. So to solve this issue, we enabled our tooling to automatically set ACLs based on list of table owners and list of downstream users that we retrieved in the preprocessor stage. Also, there are certain incompatibilities with respect to Hive and Iceberg. So one of these incompatibilities is that the underlying data file created by Hive table associates the the data columns with the column names, whereas in the Iceberg world, the columns are associated with the ordinal or ID. So this creates certain incompatibility. There are also certain nuances between required and optional fields. To deal with this, we created compatibility mode in our compute engines, and also we set certain configurations automatically as soon as the table is migrated. This is to bring parity between Hive and Iceberg. Another very interesting thing that we noticed is that some of our teams within Netflix, they implemented their own custom library that relied on certain Hive-specific features. For example, using a Hive Metastore API that deals with partitions. And this works only for Hive case. In the Iceberg case, Iceberg metadata layer itself stores the partition information. So Hive Metastore is not going to help. So, to deal with this, we had to work closely with these teams and propose changes that worked with Iceberg and then migrate their tables. Also, each team had their own migration priorities because of several reasons. So to deal with this, we created a feature within our tooling where we could set a particular schedule per table. So what that means is teams can set their own schedule priority within this migration tooling. In conclusion, in this talk, we have shared our journey of creating Iceberg and all the comprehensive ecosystem that we have built to enable its adoption within Netflix. And all the strategies that we came around Iceberg have yielded us significant benefits. For example, we are able to achieve 25% cost reduction by the virtue of Z-standard compression, efficient data cleanup using janitors, as well as data compaction provided by Autotune technology. Performance-wise, Iceberg natively outperforms Hive, where we notice that queries run orders of magnitude faster on Iceberg versus Hive. Also, the supporting systems that we built, such as Autolift technology, it helps us also improve the performance further by the virtue of data collocation. The rich metadata layer that Iceberg provides helps us to build fine-grained security controls on top of Iceberg, as well as help us build very useful abstractions such as Iceberg REST catalog. Now, these features and abstractions help us in make rapid improvements in our tech stack, where we are able to experiment rapidly with compute engines, and we could plan to replace the legacy compute engines by the newer modern compute engines. Over the time, this will lead to reduction in tech debt, improved developer productivity, as well as modernizing our overall platform. We are also developing certain other Iceberg services, such as Iceberg stats service, that creates a centralized store where it is able to collect interesting statistics with respect to accessing Iceberg tables, and it stores this history of stats. Because without this service, the Iceberg snapshots would get expired, and then you lose that history. So with this service, we are able to keep the history of these stats. And this will improve our other data systems within Netflix. For example, we are able to implement incremental data copying service that relies on this Iceberg-rich Iceberg metadata service. In conclusion, we foresee a future where Iceberg and all of its ecosystems become industry standards. And we expect every compute engine vendor to support Iceberg and all the ecosystems around it. And this will ensure that we will have fast, secure, and cost-effective data management practices across the industry. Finally, we are open sourcing our Hive to Iceberg migration tooling. This is to provide a reference to broader community, as well as to showcase how such a migration tooling can be built and used. Finally, we would like to thank Ryan Blue and Daniel Weeks for inventing Iceberg and providing us a really strong foundation to work upon. And we would like to thank all current and former Netflix stunning colleagues who have contributed to this journey in some form and shape. I would like to also thank every one of you who took time and attended our talk. Last but not the least, I would like to thank AWS for providing this terrific platform where we are able to share this whole journey with you. Thank you.